Hello, welcome to the fifth lecture of Module 1. You see, in this lecture, we'll review the concept of bending moment and shear force diagram in beam. I believe you have studied bending moment and shear force diagram in either in mechanics course, first year mechanics course, or strength of material course. What we'll do is here briefly review the concept, because the concept of bending moment and diagram will be using throughout this lecture. Okay. Now, you see, what is beam? Beam is essentially a structural element that primarily resists loads applied transverse to its longitudinal axis. Now, if you see, this is a simply supported beam. This is the longitudinal axis. Okay, this is the longitudinal axis. This is the longitudinal axis, and this beam is this structural element is subjected to load which is transverse to this axis. Okay. This kind of structure is called structural component is called beam, and when it is subjected to this kind of loading or any kind of transverse loading, it undergoes bending, right, like this. Now, you know, the internal forces developed in the beam is bending moment and shear force. Now, let's see what is bending moment and shear force. If you see, if I draw the if I take one section at a distance x from A and draw the free body diagram of this part and this part, then what happens? This is the free body diagram of this part, and then again this is the free body diagram of this part. Now, this is hinge support, so it is replaced by two reactions, AX and AY. Now, at this point, the internal forces are horizontal force, horizontal direction, in this case Fx, then vertical Vx, and then moment Mx. Similarly, in this case, this roller support is replaced by reaction By, and these are the internal forces. If you remember, in the last class we said, whenever you break a structure and at that point, that continuity of that point, when in a free body diagram, the continuity of that point needs to be represented by the internal forces, right. Now, if you draw when you draw the internal forces, sign of the internal forces needs to be taken very carefully. For instance, it is in equilibrium. When I say the object is in equilibrium, every point of the object is in equilibrium. So, this point was in equilibrium, right. This means the net force in this point, net internal forces, needs to be 0. So, therefore, if you are showing Fx in this direction for this part, you need to show Fx in the opposite direction for this part. Similarly for Vx, and similarly for moment. Now, this Vx is shear force, Mx is bending moment, and Fx is axial force. Now, what we assume here is there is no axial force. So, beam only only resists the external forces which is acting transverse in the transverse direction by bending moment and shear force. There are many cases where in a practical purposes we will see there are many cases where the any structural component may be subjected to it may be subjected to shear force, maybe bending moment, axial force together, but those kind of structural component analysis of those kind of structural component will be discussed later. Okay, but at least for this case there is no axial force, right. Now, let us define the sign convention. You see, this is our sign convention we use for bending moment and shear force. Now, what it says, you say there are two sign convention. Okay, one sign convention is the sign convention we use in the bending moment and shear force diagram, and another sign convention is the sign convention that we use when we do algebraic operation between moments and shear forces. Okay, now let us first discuss what sign convention we will use in the bending moment and shear force diagram. The sign convention in bending moment shear force diagram is this. You see, this kind of moment is called sagging moment, okay, because it causes sagging in the structure. Okay, and this kind of moment is called hogging moment. Now, one example for hogging moment is when a fisherman holds a fishing stick, then the fishing stick bends like this. Okay, these fishing sticks, the moment generated in the fishing stick is hogging moment. Now, example of sagging moment is if you take a rod and which is subjected to, or very common cloth hanging rod that we can see in household, then you might have observed that rod experiences sagging like this. In this case, the moment generated or the moment causes this is called sagging moment, this moment. Now, for shear bending moment and shear force diagram, this is positive and this is negative. Similarly, for shear force, the shear force which produces clockwise couple is considered as positive. Shear force which produces anti-clockwise couple considered as negative. Now, if you remember in the last throughout this course, we have been using, for all algebraic operation, we have been using clockwise moment as positive and anti-clockwise moment as negative, and vertical direction force as positive and horizontal direction force as negative. Means we took clockwise moment as positive, and this is positive direction and this is positive direction, right? But this sign convention we use for algebraic operation, but when we draw the bending moment and shear force diagram, we use this sign convention. Okay, whether it is a sagging moment or it is hogging moment. Okay, now so this is the sign convention, two sign convention. For bending moment diagram, this is sign convention, bending moment and shear force, and for all algebraic operation, this sign convention is positive. Okay, now let us demonstrate through some examples. Okay, now the first example is, if you take, it is a simply supported beam which is subjected to uniformly distributed load. Okay, now what we have to do is, we have to first find out the reactions at the support, then we need to determine the bending moment. The bending moment diagram is essentially the graphical representation of moment and shear force, which tells you how the moment and shear force varies along the length of the beam. Let us find out that. The first is, we need to determine the support reaction. Let us draw the free body diagram of the entire structure. Free body diagram will be, this force will be AY, and then this is AX, this is BY, and this is uniformly distributed. This is the very standard representation of uniformly distributed load, which is 10 kilonewton per meter, and this length is 3 meter. This is the free body diagram. Okay. Now, the first is summation of Fx is equal to 0, which immediately gives me Ax is equal to 0, right. Then next is, if you take summation of moment at A is equal to 0, which gives you what? Which gives you the clockwise moment due to By, which is anti-clockwise moment due to By minus 3 into By, and then plus clockwise moment due to external load. This load will be, total load is 3 into 10 multiplied by the distance, and the center of application of the resultant is 3 by 2, that is equal to 0. So, this gives me By is equal to 15 kilonewton, and similarly summation of Fy is equal to 0, which gives me Ay plus By is equal to total downward load 3 into 10, and from this equation, if we substitute By is equal to 15, we get Ay is equal to again 15 kilonewton. So, we have support reaction Ax is equal to 0, and then By is equal to 0, and then Ay is equal to 0, right. Let us find out how bending moment diagram. Now, to do so, let us take one section here at a distance x, at a distance from x from A. okay, and draw the free body diagram of this part. Now, if we draw the free body diagram of this part, this becomes this. This is AY. Ax is equal to 0, that is why there is no point to show that. Then uniformly distributed load 10 kilonewton per meter, this distance is x, and then as per our sign convention, if you remember, our sign convention was like this. Our sign convention was this moment is positive, and for shear force, this shear force and this shear force is positive, right. So, the direction of force is this here and this, okay. So, this is Vx, which is the shear force at x, and this is Mx, which is moment at a distance x from A. Now, take summation of Fy is equal to 0. Fy is equal to 0. What are the forces you have? Ay upward direction plus minus 10 into x, which is externally applied uniformly distributed load, and then minus Vx is equal to 0, right. And this gives me Ay is equal to 15, already we determined, and this gives me Vx is equal to 15 minus 10x. So, this is how the Vx varies with x. Now, then summation of say Ma is equal to 0. This gives me what? Only forces is or you can take summation of Mx is equal to 0, moment about this point, and this gives me Vx will not contribute, Ay will contribute, the external load will contribute, and the Mx itself. This gives me Mx is anti-clockwise direction, this is negative. If you remember, for all algebraic operation we use whether the sign convention will be whether it is anti-clockwise or clockwise. So, Mx is minus Mx, then plus Ay into x, and then minus 10 into x is the force which is at a distance x by 2, that is equal to 0. Okay. Now, this gives you Ay is equal to 15, we know, and this gives you Mx is equal to 15x minus 5x square. Okay. So, this is how Vx varies with x, and this is how Mx varies with x. Now, let us draw the bending moment and shear force diagram will be graphical representation of this equation along this length, and bending moment diagram will be graphical representation of this equation along this length. Now, if I do that, then yes, that was the problem. Okay, that was the A B. Now, if you Vx we obtain Vx is equal to 15 minus 10x, and Mx is equal to 15x minus 5x square. Let us first draw shear force diagram. You know, one check is you should immediately check by substituting x here. You should immediately the value of x here, which is then you can check whether it is consistent with the problem and the support condition. For instance, you see these distances, seat is simply supported beam, therefore at this point and at this point your bending moment will be 0. Let us see, if I substitute x is equal to 0, Mx is equal to 0. If I substitute x is equal to 3 here at B, then also Mx is equal to 0. So, this expression is consistent with this. Let us see whether this is consistent with or not. You see, if I substitute x is equal to 0, which gives me Vx is equal to 15. If you remember, the 15 was the support. 15 was the support reaction at A. If I substitute x is equal to 3 here, this becomes minus 15. So, again if you remember, this reaction at support B was 15, which is shown vertically upward, but in the in shear force, while showing the representing the shear force, we used this, in this case this as positive, that is why it is negative. So, these equations are consistent with the support reactions and the conditions here. Now, x is equal to 0, your bending moment is 15, and x is equal to 3, bending moment is shear force is minus 15, and throughout this length bending moment varies linearly. So, this will be the bending moment diagram, this will be the shear force diagram. This is 15, this is 15, this is also 15. I am just writing the absolute value, because below this it is understood it is negative. Okay. Now, let us draw the bending moment diagram. X is equal to 0 and x is equal to 3, bending moment is 0, and then between x is equal to 0 and 3, between A and B, bending moment varies as per this equation. If you plot it, this equation will become something like this, Okay. So, this is positive, this is positive, this is negative, right. This is shear force diagram, and this is bending moment diagram. Now, one observation here, please note that in this equation your shear force is linear and bending moment is quadratic. We are not going to make any conclusion based on this observation. Let us see other problems and how the order varies in those cases as well. Now, suppose if you have to find out what is the maximum bending moment here, maximum bending moment will be where dmax dx is equal to 0, and you will get, if you substitute that, you will get x is equal to 1.5 meter, and if you substitute x is equal to 1.5 meter here, you get m max will be 11.25 kilonewton meter. So, this will be 11.25 kilonewton meter. Another observation here, at the middle your shear force is 0, and at the middle your bending moment is maximum. So, two observations we have here is shear force is linear and the bending moment is one order higher, quadratic. Here shear force is 0 and at the same point your bending moment will be maximum. Let us see whether these observations, similar observation we have in other problems as well. Let us do one more example. Okay. Now, this is again a very this was probably the simplest example of bending moment and shear force, the first one, and if you take any book, probably the first example that gives you a simply supported beam subjected to uniformly distributed load. Let us take one more example here. It is again a simply supported beam, but it is subjected to a concentrated load. Okay. Now, again draw the bending moment diagram, your free body diagram. This is Ax, Ay, then By, this is 30 kilonewton, this is 1 meter. This is the free body diagram of AB. Free body diagram of AB. Okay. Now, again Ax will be 0, that we get directly from the first equation, summation of Fx is equal to 0, and then if you take moment about A, that is equal to 0, then this gives you 30 into 1, which is clockwise moment, minus By into 3 is equal to 0. This gives you By is equal to 10 kilonewton. And similarly, if you take Fy is equal to 0, Ay plus By is equal to 30, this gives you, substitute By is By is equal to 10, Ay is equal to 20 kilonewton. Whenever write you write force and moment, please write unit also, because this is a common mistake I have seen, that you write the value but don't then forget to mention the unit. So these are the support reactions, okay, and Ax is equal to 0 is another support reaction. Okay. Now you see this, now we need to find out the bending moment diagram and shear force diagram. First you take one section here at a distance x from A. This section is between point A and point C, between A and C. So the first case x varies from 0 to 1. Okay. Now first is x varies from 0 to 1. Okay. Now draw the your free body diagram. This is Ay, Ax is equal to 0, not showing explicitly. This is Vx and this is Mx, okay, and this distance is x. No other external load between A to C. Now this gives you summation of Fy is equal to 0. This gives you Vx is equal to Ay. Vx is equal to Ay, and Ay we already obtained 20. So this gives you Vx is equal to 20 kilonewton. So this is how Vx varies between A to C. Let's take moment at x is equal to 0. So moment at x is equal to 0 will be minus mx, because mx is anti-clockwise direction. Again and again I am repeating that when you do the algebraic operation, check whether it is clockwise or anti-clockwise. Then minus plus ay into x, that is equal to 0. Okay, and this gives you ay is equal to, this gives you mx is equal to, you see ay is equal to 20, this gives you 20 x. So this is how bending moment varies between 1 to C. Let's see what happens when you take, now you take one more section, it is section 1, then one more section here. This is again at a distance x from the x, but now in this case x varies from C to B, means x varies from 1 meter to 3 meter. So if I draw the bending moment, if I draw the this is again ay, this is 30 kilonewton, this is 1 meter, and then again this is Vx, and then this is Mx, right. Now summation of Fy is equal to 0, this gives you ay minus Vx minus 30 is equal to 0, and this gives you ay is equal to 20, we have already obtained. This gives you Vx is equal to 10, Vx is equal to minus 10 kilonewton. So this is how Vx varies between C to B, and take Mx is equal to 0 and Mx is equal to 0, ay into x, this distance is x, this distance is x, ay into x which is clockwise, ay into x which is clockwise, then minus 30 into x minus 1 which is anti-clockwise, and again minus mx which is anti-clockwise. This is 0, and this gives you ay is equal to 20. So, this gives you 20x minus 30x plus 30 minus mx is equal to 0, and mx is equal to we get minus 10x plus 30. So, this is how. Okay. Now, we have this is x, this one is x from 1 to 3 meter, 1 meter to 3 meter. Now, if you see, we have two results. This is for x between 0 to 1, and this is between 1 to 3. Now, so your distribution of shear force and bending moment between 0 to 1 is as per these equations, and distribution of bending moment and shear force between 1 to 3 meter are as per this equation. So, let us draw them, draw the bending moment and shear force. So, this was the problem. Now, it is always good practice to draw bending moment and shear force diagram just below the structure. So, you can relate bending moment and shear force to the structure. First, draw the shear force diagram. You see, between this point to this point, this is A, B, C. Between this point to this point, bending moment shear force was 20 kilonewton positive, and then between this point to this point, shear force is minus 10 kilonewton. So, bending moment shear force diagram will be at between, it is constant between this point, and then here it is minus 10. So, this is, sometime you can join them also. This is 20 and this is 10. Okay. Now, draw the bending moment diagram. Again, if you remember, this between this to this, between A to C, it is 20x. So, x is equal to 0, bending moment is 0, and x is equal to 1, bending moment becomes 20. So, this is 20, and again between this to this, bending moment diagram is this. X is equal to in this, this equation is valid for this range. So, if you substitute x is equal to 1, if you get mx is equal to 20, which is again consistent. So, there is a continuity is maintained, and x is equal to 3 if you substitute, then mx is equal to 0, it is simply supported beam. So, bending moment will be 0. Okay. Now, this is bending moment diagram, and this is shear force diagram. Okay. Now, let us see what is the observation. Bending moment is, shear force is constant, bending moment is one order higher, linear. In this case, bending shear force is constant, bending moment is one order higher, linear. Again, bending moment and shear force diagram, you see at this point your bending moment is positive, and then bending moment is maximum. Here it is just at this point your shear force is changing sign. Okay. One another point to be noted, as I said, it is a good practice to draw bending moment and shear force diagram just below the structure. You see, what was the value of this force? It was 30 kilonewton, right? 30 kilonewton, which is downward. You see, this is 20 and this is 10. 20 plus 10 is equal to 30 kilonewton. So, since there was a concentrated load here, and because of the load, bending moment is, shear force is constant throughout, and suddenly you have a concentrated load, and therefore, there is a sudden change in sign of the bending moment, or sudden drop in, or sudden increase in bending, sudden change in shear force, and that change will be according to the value of this load. So, this is reflected in bending in shear force diagram. Okay. Now, for today, that's all. We'll have one tutorial class. We'll try to have some more example on bending moment and shear force diagram. Thank you.